Now, as we go along learning about different types of forces, we're going to keep incorporating the forces that we have previously talked about. So we talked about gravitational force, and this is the one that's always going to be hidden in our problems. Anytime we have an object, there's going to be a gravitational force on it. So in all of our problems from this point on, you should consider the gravitational force acting on the object. The next type of force we're going to talk about is normal force. This does not mean it's ordinary. Normal, the mathematical definition of the word normal means that it is perpendicular. Normal, perpendicular, orthogonal, those are all synonyms. So whenever two surfaces are in contact, they exert a normal force on each other, and that normal force always acts perpendicular to the surface. So what force allows you to jump? Well, that is the normal force. You exert a downward normal force on the ground with your feet, and then, as according to Newton's third law, then the ground exerts an upward normal force on you, and that is what enables you to jump upward, and gravity is working, gravitational force is working against that, etc. I would like to point out, so if you have an object just sitting on a flat surface and it's just chilling out there and nothing's happening, there's a gravitational force acting on the object, there's a normal force acting on the object. Okay, for an object at rest, you know, it's just chilling out there, Newton's second law becomes normal force minus mg equals 0. So in these situations where an object is on this flat surface, normal force winds up being equal in magnitude to gravitational force. However, students have a tendency to get stuck in this mindset and always plug in mg for normal force. And that is not true. If the floor is angled, if there are other vertical forces acting, like if I push down on this box, or maybe it's up against a wall or a ceiling or something, in any of those cases, normal force is not equal to mg. Normal force is equal to mg when an object is on a flat surface and there are no other forces acting in the vertical direction. Okay, so in that special case, normal force is equal in magnitude to gravitational force. I would also like to point out that normal and gravitational forces are not an action-reaction pair. The gravitational force the Earth exerts on an object is paired with the gravitational force the object exerts on the Earth. That is an action-reaction pair. The normal force the floor exerts on the object is an action-reaction pair with the normal force the object exerts back downward on the floor. Okay? Action-reaction pairs, you never wind up adding together because one part of the pair is a force acting on object 2 because of object 1, and the other force is a force acting on object 1 because of object 2. They're not acting on the same object, so we never will wind up adding up forces that are action-reaction pairs. So, let's take this example problem. Man with the mass 75 kilograms pushes downward on the floor with a force of 820 newtons. What is his acceleration? Well, always draw a picture. Got our guy on the floor. He pushes downward on the floor with a force of 820 newtons. Well, what does that mean? According to Newton's third law, the floor exerts a reaction force, 820 newtons, that acts upward on him. What other forces are present? Well, we've got gravity. Gravitational force acting downward. That's it. So, we go to write Newton's second law. In the y direction, nothing's really happening. In the x direction, in the y direction, we have normal force upward, gravitational force downward. So normal force minus mg equals mass times acceleration. And we can solve this. Acceleration is what we're trying to find. So doing a little bit of algebra, we can see acceleration is normal force minus mg divided by mass, and then we can plug in numbers. Acceleration in the y direction is normal force, which is 820 newtons, minus mass times g divided by mass. And doing some quick calculation shows us that our acceleration is 1.13 meters per second squared. We called up positive, this came out positive, so its acceleration is 1.13 meters per second squared upward, perhaps using the process of jumping. He's got his legs bent, pushing off the ground, something along those lines. So even here we see a situation where normal force is not equal to gravitational force. They're unbalanced because this guy is accelerating upward. All right. Apparent weight is what a scale reads. What a scale actually knows is how much upward force it is exerting on you, or how much force you are exerting on it. Same thing. But what a scale actually reads is normal force. You may have noticed this if you step on a scale. When you're just standing there, it tells you your weight or your mass. If it tells you your mass, what it's actually calculating is a force, and then it's calibrated to divide by 9.8 to figure out what your mass actually is. But you may have noticed, like when you first step on, it spikes up and is higher than your actual weight, or as you're stepping off, it's higher than your actual weight. If you jump on a scale, it will temporarily read a value that is higher than your weight because it is measuring the normal force that the scale is exerting on you. So different places where your apparent weight can change. One of you felt lighter, felt like you were floating. Think about that for a second. Well, there are a couple different times when you might have experienced this. The two that immediately come to mind for me is on a roller coaster. When you go down that first hill, you feel like you're kind of floating, or if you go up, if you go up and come back over, when you're at this high point, you feel like you're floating for a while. And the other time when you might have noticed this happen is on an elevator. When an elevator starts moving downward or stops moving upward, you kind of get that those flutteries in your stomach, and you feel like you're way a little bit less. Well, what you're feeling essentially is your apparent weight. This is also what's actually happening with 0g. Again, if there is no normal force acting on you because you're accelerating at the same rate as the box that you're in, like the spaceship that you're in, then the normal force is what we can actually sense. We can't really feel gravitational force directly. We feel it because we feel the floor pushing up on us, on our feet. If there isn't anything that we're touching that's pushing on us, we can't feel that force. So that's why we experience 0g, quote unquote, out in space, because there is no normal force that the floor or I guess there is no set floor, but the sides of the spacecraft are exerting on us. Not us, maybe someday, but astronauts in general. So again, apparent weight is normal force. So for example, we've got a man with mass 82 kilograms, excuse me, is riding on an elevator that is accelerating upward at 2.1 meters per second squared. What is his apparent weight? Well, what's happening? We've got an elevator, we got a dude, the elevator is accelerating upward. What are the forces acting on him? Well, it's always gravitational force, and the other force acting on him is normal force from the floor of the elevator. If you consider the elevator, there's probably some upward force from like the cables or whatever that hold up the elevator, and then there's gravitational force. But on the guy, there's normal force from the floor, gravitational force going downward. Apparent weight is normal force. So normal force is what we're trying to find. And our equation for Newton's second law is exactly the same as it was over here. We've got normal force minus mg equals mass times acceleration. So normal force equals ma plus mg. We've defined up to be positive. Our acceleration is up. So when we plug this in, 82 times acceleration is 2.1 plus 9.8. Factor that, and we can then calculate normal force, which comes out to be 975.8 newtons. And that is this man's apparent weight in the elevator. All right, now if the same man is standing on a scale, the scale reads 78 kilograms, what is the man's acceleration? Well, same guy, same forces. Now the scale, if it's reading in kilograms, the scale is calibrated to divide by 9.8. So if the scale reads 78 kilograms, what that means is that the normal force is actually, the normal force is actually 78 times 9.8. The scale assumes you're just sitting there at rest when it figures out your mass. So once again, we can say Fn minus mg equals ma. Acceleration is normal minus mg over m. So we've got 78 times 9.8 minus 82, which is his actual mass, times 9.8 over his mass again, 82. And we can figure out what the acceleration is. 78 times 9.8 minus 82 times 9.8 divided by 82. We get the acceleration is minus 0.47, whatever. So that's about 0.478 meters per second squared. And the negative tells us that we are accelerating downward. Right? Keep in mind that doesn't mean we're moving downward. We could be going upward and slowing down, or we could be going downward and speeding up. Either could be the case. So that's how we deal with apparent weight. Notice in our expression for apparent weight, if the acceleration of the object we're in and gravitational acceleration were the same value, well, equal and opposite, I should say, then we would be experiencing weightlessness. If we're accelerating downward at 9.8 meters per second squared, the normal force would be 0, and so our apparent weight would be 0. And that is what is really happening when we experience quote-unquote 0 g.